Hello everyone. In today's video, I'm going to talk about recursion. The word does give away a lot. It means something that keeps recurring. So in a programmer's lingo, it just means a function that keeps calling itself. To better imagine it, think about those special Russian dolls you see in spy movies. But forget about the spy portion and think about how the spy has to open the doll only to find another doll inside, and then another, and then another, and then another, and it continues for some time. The same thing happens with a recursive function. It will keep calling the same function till I get the desired result. So how will I know that I got the desired result? In other words, in a function that keeps calling itself, how can I tell when to stop? To exit a recursive function, I need to have a base case. This will act as an exit to the recursive function. The other thing that I need to have is a recurring function that will be making progress towards reaching that base case. So let's dive into an example to understand this better. Factorials. We are going to understand about recursion using factorials. So any factorial can be represented like this, which is 5 factorial is equal to 5 cross 4 into 3 cross 2 cross 1. Now, this can be also written as 5 factorial is equal to 5 cross 4 factorial. 4 factorial is equal to 4 cross 3 factorial. 3 factorial is equal to 3 cross 2 factorial. 2 factorial is equal to 2 cross 1 factorial. And 1 factorial is just 1. So if I try to write it as an expression, it will be n factorial is equal to n cross n minus 1 factorial. Okay, so now that we have the recursive function with us, we need to know the base case to understand when to stop. So I will consider two cases, either a 0 factorial or a 1 factorial. Both will result in a 1. And now coming to the function, start with defining the function, which is factorial. It takes n as the parameter. N will be an integer. We don't have to explicitly say that out in Python, but yes, Python can interpret it by seeing what we are trying to do with the value. So as we enter the function, we check if we have reached the base case or not, which is if n is equal to 1 or n is equal to 0. And if that is the case, we just return 1. And at the end of this function, we just return n into factorial n minus 1. This is the recursive function right here. If we give it a bunch of inputs, we can see how fast our algorithm really is. So if you start at 5, for example, that is good. 10 is also good. 50 is also good. 100 is good. And 1000 is where we are having an issue. And the error we get is the maximum recursion depth exceeded while calling a Python object. So that is interesting. Python self-checks the number of activations on a function, and if the maximum depth exceeds Python's default value, we get an error. This is done in order to save our resources on our CPU, and an additional call also requires additional memory. However, you can change the defaults using the following function. So when we called our factorial function, the recursive tree looks like this. This is a linear recursion tree, meaning it tries to go in one direction and then traverses back in the same direction. So in this case, the time complexity is not that nested. The time complexity for this recursive function would be O of n. It's not that different when we think about the iterative approach. There, the time complexity will also be O of n, as the function is dependent on the nth Fibonacci number. The space complexity, on the other hand, is calculated a bit differently if it's a recursive approach versus if it's an iterative approach. In a recursive approach, a new memory will be invoked every time the function is called. So the space complexity is going to be O of n. The space complexity for an iterative approach, on the other hand, is simple. We are reusing the variable that is computing values every iteration. So in each iteration, the previously computed value in memory can be erased anytime, as the variable would be pointing to a new value in a memory. So in this iterative approach, the space complexity will be O of 1, which is constant. This was for a linear function. Imagine instead of calling the recursive function once, we have to call the recursive function twice. So we have the famous case of the Fibonacci sequence to understand that. The Fibonacci sequence goes like this. It has 1,
2, 3, 5, 8, and 13.
If you want to represent this in the form of a function, then it would look something like this. F of n is equal to f of n minus 1 plus f of n minus 2. Here, each time a function is called, it will invoke two other functions. And so it will be called a binary recursion. The recursion trace will look something like this. So if I define a function called Fibonacci recursion, it takes n as the input. And in this case, our base case will be if n is equal to 1 or n is equal to 2, then we just return 1. And our recursive function will be Fibonacci recursion of n minus 1 and Fibonacci recursion of n minus 2. And this is something that we will return at the end of each function call. So if you compare some of the input values, let's say we start at 5. We see that 5 was quick. We then take 10. That was not quick. We then take 50. That is taking forever. So, if the calls are increased from linear to binary, the time complexity has almost increased exponentially. This is because every time a function is invoked, f of n will be calculated every time. So, as we can see in this diagram, each value is repeated multiple times. Imagine calculating each value again and again. How many nested calls will be made? The larger the number, the larger the nested calls will be. For the binary recursion for this Fibonacci function, the time complexity will be O of 2 raised to n. The space complexity is, I thought, would be the same, but that is actually not the case. Here, the space is utilized using the stack approach. I'm not sure if the approach for recursion is implemented in the same manner as it is implemented in C, but the best explanation I had found was written for the C language. I will probably have to look more into how it's done in Python, but that's for another time. The point is, the space complexity will be dependent on the depth of the tree, which will be O of n. In our case, it would be O of log of 2 raised to n, which will come out to be O of n. The guy has pointed out really well that it is in fact sequential and not plain recursive as it looks when we look at the tree diagram. My point is, it takes a really long time to compute when the value is really large. Because when we reach 30, it takes these many function calls to get the final value. This is not efficient. To solve this problem, we can store the values that we have just computed and use them. This method is called memoization. It's basically like caching. What it does, it stores the values that we have previously computed to save our processor from taking the load, and instead the values can be called from the cache, in our case a dictionary. The implementation of that will look like this. The time complexity here will be reduced to O of n because there will not be recursive calls in each function call. The space complexity will also be O of n. There could be functions that can have more than 2 recursive calls. The time complexity of such functions will be even more complex than what we saw for our functions before. Okay, that was a long talk for recursion for today. I will cover more about recursion also in some other videos, but for now that was it. Till then, thank you so much for watching this one, and please let me know in the comments below if you like my video, and do subscribe to my channel. Thank you and bye.